In the middle of June 2026, a press release went out claiming that an artificial intelligence system had just achieved one of the most difficult, most sought-after milestones in the entire history of computing, years ahead of schedule, using nothing more exotic than rented cloud access to existing quantum hardware. If true, it would mean a problem that companies with tens of billions of dollars in dedicated research funding still describe as years away had just been quietly solved by a comparatively small AI firm, almost in passing. It was not true, or at least it has not been independently verified by anyone outside the company that made the claim. But buried underneath that one overhyped announcement is a genuinely fascinating set of real, peer-reviewed quantum computing breakthroughs that actually happened in the past several months. And separating the real discoveries from the inflated one turns out to be the most interesting part of this entire story. Let's go through the actual evidence, one claim at a time. Claim 1, and this is the genuinely real one. In October of 2025, Google's quantum computing division published a peer-reviewed paper in the scientific journal Nature, demonstrating what they called the first verifiable quantum advantage, running an algorithm called quantum echoes on their Willow superconducting processor. Unlike earlier, more contested claims of quantum supremacy, where classical computer scientists later found faster classical workarounds that undercut the original claims, quantum echoes was specifically designed so its results could be independently checked and cross-confirmed by other quantum hardware of similar quality. The headline number is striking on its own. The algorithm ran roughly 13,000 times faster on Willow than the best available method running on one of the fastest classical supercomputers on the planet. But the more scientifically meaningful part of the announcement came from a follow-up collaboration with researchers at the University of California, Berkeley, who used the technique as what they called a molecular ruler, applying it to two real organic molecules and successfully matching the results against actual laboratory nuclear magnetic resonance measurements, while also extracting some additional structural detail that conventional NMR alone struggled to capture. Verified, peer-reviewed, and genuinely useful for a specific, narrow category of chemistry problem. This one holds up. Claim 2, equally real, comes from an entirely different field in an entirely different country. Physicists Eric Lutz and Milton Aguilar at the University of Stuttgart published research showing that microscopic quantum heat engines can exceed the famous Carnot efficiency limit, a foundational rule of thermodynamics established roughly 200 years ago that sets the theoretical maximum efficiency for converting heat into mechanical work. Headlines describing this as physicists breaking a 200-year-old law of physics aren't exactly wrong, but they skip past the actual explanation, which turns out to be more precise and, frankly, more interesting than a simple rule-breaking story. The Carnot limit was derived for large classical systems, with no concept of quantum correlation built into its mathematics at all. At the scale of individual atoms and particles, quantum correlations between particles become a real physical resource, on top of ordinary heat, that a sufficiently small engine can tap into to produce additional work. The old limit doesn't actually get violated in the sense of creating energy from nothing. It gets extended, accounting for a genuine physical resource that simply did not exist in the classical picture the original limit was built around. Genuinely surprising, genuinely real, peer-reviewed, and explainable without needing to invoke anything mystical. Claim 3, also real, though less flashy than the previous two. In June of 2026, IBM announced it would invest more than $10 billion in quantum computing research and infrastructure over the following 5 years, building toward what the company describes as the world's first large-scale fault-tolerant quantum computer, targeted for delivery in 2029. That's a meaningful detail worth sitting with for a moment. Even IBM, operating the largest fleet of quantum computers in the world with more than 90 systems deployed globally, and a client network exceeding 340 organizations actively running real workloads today, describes full fault tolerance as a target 3 years out, not something already achieved. The company points to genuine, verifiable progress supporting that timeline, including collaborative work simulating a protein with more than 12,000 atoms alongside researchers at the Cleveland Clinic and Japan's Riken Institute, and research helping confirm the structure of a previously unobserved molecule. Real progress, clearly documented, with a clearly stated multi-year runway still ahead of it. Claim 4, also genuinely real and worth understanding on its own terms. In the same month, Microsoft reported a significant advance in its Majorana 2 quantum processor, a chip built around an exotic and historically controversial approach using something called topological qubits, which in theory offer inherent protection against the errors that plague most other quantum computing hardware designs. By replacing aluminum with lead in the chip's superconducting material, Microsoft's team more than doubled the protective energy gap shielding these fragile quantum states and extended how long certain quantum properties could be reliably maintained, improving what researchers call parity lifetimes by more than 1,000-fold, from a matter of milliseconds to over 20 seconds. It's worth noting honestly that Microsoft's topological qubit approach has faced sustained scrutiny from the broader physics community, particularly following the company's 2025 announcement of its earlier Majorana 1 chip, which prompted significant debate over whether the evidence fully supported the specific exotic quantum states Microsoft claimed to have created. The June 2026 update represents real, measurable improvement on the company's own hardware metrics, while the underlying physics claim remains an area of genuine, ongoing scientific debate rather than settled consensus, a distinction worth holding on to rather than glossing over in either direction. And now, Claim 5, the one that actually inspired the godlike discovery framing in the first place, and the one that doesn't hold up to the same scrutiny as the previous 4. In mid-June of 2026, a company called AIX Global Innovations released a 100-page technical report through a commercial press release wire service, claiming that its proprietary artificial intelligence system, described as an adaptive multi-agent control engine, had achieved fault-tolerant quantum computing, using ordinary rented access to existing IBM quantum hardware through IBM's standard commercial cloud service, a result the company claimed made quantum computing possible today, rather than the 3 to 5 years away that the rest of the field, including IBM itself, continues to project. The announcement was timed to coincide with a quantum industry conference in London, and it described the company's own AI software, not any new physical hardware, as the breakthrough responsible for clearing fault tolerance requirements that companies with vastly larger research budgets and dedicated physics teams have spent years working toward without claiming to have crossed that line. Here is precisely why this particular claim deserves a different level of scrutiny than the previous 4. It was not published in a peer-reviewed scientific journal. It was not independently verified by any outside research institution, university physics department, or competing quantum computing company at the time of the announcement. It was issued through a business wire service designed for corporate press releases and financial announcements, the same channel companies use to announce earnings results or product launches, not the channel through which genuine scientific breakthroughs are typically first introduced to the world. And the claim itself runs directly counter to the carefully documented, consistently cautious timelines being published by every major, independently verified quantum hardware program currently operating, including companies with vastly more resources, more physicists, and more publicly scrutinized track records than the company making this particular claim. None of that proves the claim is false. It does mean that until something resembling independent verification actually shows up, treating it with the same confidence as the 4 peer-reviewed, independently confirmed results above would be a mistake. So here's where this investigation actually lands. Quantum computing in 2026 is producing real, exciting, independently verifiable progress. A peer-reviewed, verifiable quantum advantage with genuine chemistry applications, a careful and surprising extension of 2-century-old thermodynamic theory, a major hardware company committing $10 billion toward a clearly stated 2029 milestone, and real eyes, if scientifically contested, hardware progress from a company pursuing an unusually exotic qubit design. What it has not produced, despite what one particular press release wants you to believe, is a single AI system quietly leapfrogging the entire well-funded, heavily scrutinized global quantum computing industry using nothing more than rented cloud access and a clever piece of software. The real story here was never short on genuine wonder. It just required actually checking which claims came with peer review and independent verification, and which ones came with a press release and a conference invitation instead. It's worth taking one more pass at exactly why the verification gap between Claim 5 and the first 4 claims matters so much. Because the difference isn't just procedural pickiness about where research gets published. Peer review, for all its well-documented flaws and slowness, exists specifically to catch the kinds of errors and overstatements that are easy for any single research team, however well-intentioned, to miss when evaluating their own work. A claim that a system has cleared all the requirements for fault-tolerant quantum computing is, by the field's own definition, an extraordinarily specific and demanding technical bar, requiring error rates below a precise mathematical threshold, demonstrated and reproduced across multiple independent runs, and ideally confirmed by researchers outside the team that built the system in the first place. The AIX announcement describes internal validation, 22,500 circuits run across company, controlled testing, with results interpreted and reported entirely by the company's own team. That is meaningfully different from Google's Quantum Echoes result, checked against independent, real-world NMR laboratory data gathered by a separate university research group, or from IBM's protein folding collaboration, conducted jointly with the Cleveland Clinic and a Japanese National Research Institute, each bringing independent expertise, an independent incentive to get the underlying physics right, rather than simply confirming a press-ready headline. There's also a useful pattern worth recognizing here that extends well beyond this one specific announcement, because it shows up reliably whenever a fast-moving, genuinely exciting scientific field starts attracting serious public attention and serious investment money at the same time. The more genuinely impressive and well-funded a field becomes, the more incentive exists for smaller or less established players to claim a shortcut past the years of incremental, expensive, carefully verified work that the major, well-resourced labs are still grinding through. That dynamic isn't unique to quantum computing. It shows up in biotech, in battery technology, in nearly every frontier, science generating both genuine breakthroughs and genuine investor enthusiasm at the same time. The practical lesson isn't to distrust every exciting announcement equally. It's to specifically check whether a given claim has cleared the bar the rest of its own field actually uses to evaluate similar claims. Peer review, independent replication, and scrutiny from researchers with no financial stake in the announcement landing well. 4 of the 5 claims investigated here cleared that bar without difficulty. The 5th one, so far, has not. It's also worth giving the real science one more moment in the spotlight before wrapping up, because the 4 verified breakthroughs deserve to be remembered as the actual headline here, not as a footnote to the one overhyped claim that briefly stole the spotlight. Atom computing, working with a completely different hardware approach based on individually trapped neutral atoms, rather than superconducting circuits or topological states, has separately reported building systems scaling toward more than 10,000 physical qubits, estimated to eventually yield more than 100 error-corrected logical qubits, placing neutral atom hardware among the more credible near-term paths toward practical fault tolerance, according to independent industry analysts tracking the entire field side by side. Multiple distinct hardware approaches, superconducting, trapped ion, photonic, neutral atom, and topological, are all advancing in parallel, each with genuine strengths and genuine open challenges, which is itself a healthy sign for a field this early in its development. No single company, and certainly no single press release, gets to declare the race finished while 4 or 5 genuinely different, genuinely competitive approaches are all still making real, independently documented progress at the same time. So if you came across the godlike discovery headline first, before any of the actual context behind it, here's the honest summary worth carrying away. Quantum computing is not stuck. It is not stagnant, and it is most certainly not boring. It produced, in the span of less than a year, a peer-reviewed, verifiable quantum advantage with a real chemistry application, a genuine extension of 2-century-old thermodynamic theory, a $10 billion corporate commitment backed by a specific public timeline, and continued hardware progress across at least 4 genuinely distinct competing technical approaches. What it did not produce, despite one particular announcement's confident wording, was a single AI system quietly solving fault tolerance years ahead of an entire global industry's combined research effort, using nothing more than a clever piece of software and rented cloud access. The real story was never short on wonder. It just required checking carefully which parts of it had actually been verified and which parts simply wanted you to believe they had.